Hi everyone, so in this video I just want to talk a little bit about how to do the calculation for the gravimetric analysis lab, okay? And I'm going to do the calculation based on the problem that's shown here. So you remember that the experiment requires you to weigh an unknown sulfate salt, and in this case you weigh that unknown sulfate salt to be 0.343 grams, and then remember that you carry out a reaction to precipitate the sulfate part of that unknown sulfate salt. And so you dissolve it, in this case in 50 milliliter water, you add HCl to help it form the crystals. Remember, the HCl is not a reactant. You heat it, and then at the end, you isolate this precipitate that is formed because of the reaction between the sulfate and the barium, which is the barium sulfate. And in this case, the precipitate, once you filter and heat the paper away, turns out to weigh 0.666 grams. So the question then is, what is the cation that was originally present in the unknown sulfate salt? So in general, you can represent the reaction between the unknown sulfate salt and barium chloride as follows. If your cation happens to have a +1 charge, because sulfate is -2, you're going to need to have two of those cations. So then it's M2SO4 plus BaCl2 forming BaSO4 and MCl. If your unknown cation is a +2 charge, then it's going to be MSO4 plus BaCl2 forming BaSO4 and MCl2. You notice then either way, you always get BaSO4 on this side. Just to restate the problem, we have 0.666 gram of that barium sulfate, or the white precipitate, and originally we weigh 0.343 grams of the unknown sulfate, and again it could be either one of these formulas. There are two ways to solve this problem. One way would be to use a mole-to-mole relationship between the barium sulfate and the unknown sulfate. But what I want you to try to do in this case is actually to use percent composition to solve the problem, and I'm going to explain in this video how to do that. The first thing to remember, of course, is that we use the unknown sulfate in such a way that it becomes the limiting reactant, whereas the barium chloride is in excess. If that's the case, that means that all the unknown sulfate is used up in the reaction, that's the definition of a limiting reactant, to form barium sulfate, right? Because the sulfate here would get converted to the sulfate in barium sulfate, okay? So another way I can say this is to say all the sulfate in barium sulfate should equal the mass of sulfate in the unknown sulfate. So for example, if I have 1 gram of sulfate in my barium sulfate, I should also have 1 gram of sulfate in my unknown sulfate. This is a concept that's exactly identical to the concept we use to solve for molecular and empirical formulas in combustion analysis. If you remember, in that context, we have an organic compound, which is our unknown, and we have excess oxygen. So we make our organic compound the limiting reactant, and then we produce CO2 and H2O. And remember, what we said there is that we said all the carbon in CO2 is the same as the mass of carbon in the organic compound, and the mass of hydrogen in H2O is the same as the mass of hydrogen in the organic compound. So notice that the two approaches here are exactly identical, and it's just stoichiometry of using limiting reactants. So once you understand that the mass of sulfate in the barium sulfate is the same as the mass of sulfate in the unknown sulfate, then what I can do is first calculate how much sulfate I have in my barium sulfate. Well, that is not a difficult calculation to do, because we can use the concept of percent composition to help us calculate out how much sulfate is in there. And to do that is just by using this equation. I would use percent sulfate in barium sulfate and multiply by the mass of barium sulfate that I have. Remember that percent sulfate in barium sulfate would just be given as the molar mass of sulfate over the molar mass of the compound times 100%, then multiply that with 0.666, which is the mass of barium sulfate that you get. If you plug in all the numbers, what you're going to get at the end is 0.2744 grams of sulfate only. Remember what we said earlier. That is the same mass as the mass of sulfate in the unknown sulfate, because our unknown sulfate is the limiting reactant. So in other words, the mass of sulfate in the unknown sulfate is also 0.2744 grams. Okay, now how do we use this information to figure out what our unknown sulfate is? Well, we can use another definition of percent composition in this case. If you remember back the concept of percent composition, there are two definitions that we can use to calculate percent composition. One was the one that we used in the previous slide, which is using molar masses. But another way to get percent composition is to use actual masses. So for example, in this case, if I want to calculate percent sulfate in my unknown sulfate salt, I can just use the mass of sulfate I have in my unknown sulfate salt, which is this number right there, divided by the total mass of my unknown sulfate. Well, I know that number because I weigh the mass of the unknown sulfate at the beginning. If I were to take the ratio of those two numbers multiplied by 100%, then I get the percent sulfate in my unknown sulfate salt. Notice that this is slightly different than calculating percent composition using molar masses, because in this case we're just using the mass that we measured experimentally. If I plug in the numbers for those two masses, what I get is 80% sulfate in my unknown sulfate salt. Here's where things might be a little tricky. Once I figure out that my unknown salt contains 80% sulfate, I want to go back to that other definition of percent composition, which is using molar masses. In this case, I would say I know the percent sulfate is 80%, and it could be calculated by using molar masses. Molar mass of sulfate in the unknown over molar mass of the unknown, which remember is really the thing we're looking for here to figure out the identity of the unknown, right? So molar mass of the sulfate over molar mass of the unknown should equal 80%. If I do a little algebra here to solve for the molar mass of unknown, what I get is molar mass of unknown is equal to molar mass of sulfate times 100 over 80. Well, I know what molar mass of sulfate is. It's 96. So it's 96 times 100 over 80, which gives me 120 grams per mole for the molar mass of the unknown. From here, I want to try to figure out what my M, my metal cation, is. And remember that there are two formulas that are possible, M2SO4 or MSO4. Okay? If my formula is M2SO4, then to solve, what I need to do is solve for the molar mass of the M itself, which remember that the molar mass of the unknown, if the formula is this, would be 2 times the molar mass of M plus the molar mass of sulfate as shown here. So I can then isolate and solve for just the molar mass of M, which is going to be 24 over 2, which is going to be 12. Now, at this point, you need to look at the formula itself. Because the formula is M2SO4, we said earlier that that means the cation must be a +1 cation, okay? And if it's a +1 cation, it's going to be in group 1A in the periodic table. So what you need to do there is then go to the periodic table and see if there's anything in group 1A that has a molar mass of 12 grams per mole. If you do that, you'll find that nothing gives you 12 grams per mole in group 1A, so that means that this is not the correct formula to use for your unknown sulfate salt. Alternative is to use MSO4. In this case, the molar mass of M would just be 24 because there's only one M. And since given this formula, we know that M is a +2 cation, we go to the periodic table, look up all the +2 cations and see which one has a molar mass of 24. In this case, we find that magnesium is the cation. So then our unknown is magnesium sulfate. Okay, so this is how you're going to solve for the identity of the unknown in the gravimetric analysis lab.